In Chapter 3, Section 4, we're looking at linear inequalities in two variables. Before, we looked at linear equations. Now we're looking at inequalities. Our objectives are to graph linear inequalities in two variables and graph the intersection of two linear inequalities. These graphs are going to appear as lines with some shaded regions to indicate the solution to the linear inequality. An inequality can be written as ax plus by is less than c. Remember that a linear equation in standard form is ax plus by equals c. So we're looking at the inequalities, the ones that are not equal. And if it's not equal, it could either be less than or equal, or greater than or equal. And a, b, and c are real numbers. A and b cannot both equal 0. And we call this a linear inequality in two variables. We use a three-step process for graphing linear inequalities. By now you've practiced graphing linear equations by finding a point and a slope, or by finding 2 points, by finding the intercepts. So you have practiced graphing the linear equations. So what we're going to do in graphing linear inequalities is to do this three-step process. The first step is to draw the graph of the straight line that is the boundary. Now, if our inequality has a less than or equal to or greater than or equal to, the line that we're going to draw is going to be a solid line. If the inequality involves a less than or greater than, instead of drawing a solid line, we're going to be drawing a dashed line. Step number 2 is to choose a test point. Now, you want to choose any point that's not on the line and substitute the coordinates of this point into the inequality. And one point, which I tend to choose most often, is the origin. And the origin coordinates are 0, 0. So you would plug in 0 for x and 0 for y and determine if the inequality is true. And the only time you don't want to choose the origin is if the line actually goes through the origin. So you would have to pick an alternate point. In any case, you want to shade the appropriate region. You're going to shade the region that includes a test point if that test point satisfies the original inequality. In other words, if the inequality is true. Otherwise, you're going to shade the region on the other side of the boundary line. Let's look at this example where we're asked to graph the inequality 2x plus 3y is less than or equal to 6. You want to first graph the boundary line, either by finding the x and y intercepts or rewriting the inequality in terms of y equals mx plus b. So let's begin by graphing finding a point and a slope by getting this inequality in terms of y equals mx plus b. So our boundary line is going to be the equation 2x plus 3y is equal to 6. This is a linear equation. One way to graph a linear equation is by writing this in the form of y equals mx plus b. So you can identify the slope and the y-intercept. To do that, I'm going to first subtract 2x from both sides, resulting in the equation 3y equals negative 2x plus 6. Divide both sides by 3 and simplify the equation to get y equals negative 2/3 x. Divide both of these by 3, negative 2/3 x plus 2. Now you can identify the slope, which is negative 2/3, and remember the slope is the rise over the run. And you can also identify the y-intercept, which in this case is equal to 2. So the point 0, 2 is the y-intercept. You begin by plotting a point on the y-intercept of 0, 2, and finding another point using the slope of negative 2. So from this point, you're going to move 2 units down and 3 units to the right. So that is another point that's on the line. We also need to determine if the boundary line is solid. Because the inequality is less than or equal to, that means we're going to have a solid boundary line. So let's graph the line that goes through those 2 points. So we have the graph of our boundary line, and the boundary line consists of really an infinite number of points. Every single point that appears on this line is actually a solution to the inequality. You could plug any number into the original inequality and see that that inequality would be true. Now this boundary line divides our graph paper into 2 regions, a region that's above the line and a region that's below the line. There's a whole group of other points that also satisfies the inequality, and we have to determine if all those points are above or below the inequality, the boundary line. So to do that, we're going to pick a test point. Again, the point that I like to pick is that point that's at the origin. If I plug in this into the original inequality and it's true, that means that origin is a solution to the inequality, and all the other points that are on the same side of that line would also be true. If the origin, when you plug it in, ends up being false, that means that would not be a solution, and any of the other points in this region would not be satisfy the inequality. So you would have to shade the other side of the line. So let's look at picking our test point and testing it. So the point we're choosing to test is the point 0, 0. And I'm going to plug that back into the original inequality. The inequality is 2x plus 3y is less than or equal to 6. By plugging in a 0 for x and a 0 for y, we get 2 times 0 plus 3 times 0. Is that less than or equal to 6? Well, by simplifying, we get 0 plus 0. 0 is less than or equal to 6, so we say that that is true. That test point does satisfy the inequality, so that is part of the solution to the inequality. There are an infinite number of solutions, and that is one of them. So what we'll do is we'll shade all the points that are on the same side of that test point. And this is a good time, if you're doing this in your notebook, is to use a highlighter. So every single point that is below that line and all the points that are on the line are solutions to the inequality. There's really an infinite number of x and y values that make this inequality true. Everything that's on the other side of that line would end up being false. For example, if you chose a different test point, say you chose say this point right here, where x is 2 and y is 3, we should find that that would be false in the original inequality. So let's look at testing that point, which is 2, 3. By putting it back into the original inequality, we get 2x, and we're replacing the x with the 2, plus 3 times the y that I in my test point. Is that less than or equal to 6? Is 4 plus 9 less than or equal to 6? Well, this is false. So the fact that this point over here on this side of the line, of that boundary line, is false, we know that all of the other points that are near it on that same side of the line are also false.